India has quickly become the world's second largest consumer of artificial intelligence. This chart shows the global distribution of ChatGPT users. Right behind the United States, India captures 19% of the total user base, leaving countries like Brazil and the UK far behind. But there's a stark divide between using this technology and actually owning it. Public market listings show zero native Indian AI software giants or algorithm developers. We are buying the end product, but we do not own the code or the hardware driving it. If the country isn't building the software, where exactly is all that multi-billion dollar domestic AI investment actually going? The answer requires looking past the screen. The real Indian AI trade is grounded in physical assets: large tracts of land, specialized cooling systems, and uninterrupted gigawatts of electricity. To keep the so-called cloud functioning at a global scale, it relies on heavy-duty industrial engines working continuously to prevent the hardware from melting down. To understand where the capital is flowing, we have to stop looking at the digital endpoint on our phones and start looking at the heavy, physical bedrock making it possible. This chart shows the shift in data center workload composition. By 2030, the share of capacity dedicated purely to computationally heavy AI tasks is projected to expand from 15% up to 35%. This matters because of a metric called rack power density, which simply measures how much electricity a single server rack consumes. A traditional internet server rack requires about 5 to 15 kilowatts of power. AI workloads rely on high-density GPU clusters. That pushes the requirement per rack up to 25 to 40 kilowatts, a 3 to 5 times multiplier over the old standard. This diagram maps data center power flow. Electricity flows from the grid to the servers, taking 40 to 50% of the draw. Because AI processors run hot, another 40% is burned purely on roof cooling systems, just to maintain ambient temperature. This jump in density shifts AI expansion away from the keyboard and into the realm of extreme physical engineering and power generation. When you scale that math up to a national level, the infrastructure requirements become staggering. As of 2025, India's installed data center capacity sits at about 1.3 gigawatts. This chart shows the projected growth trajectory over the remainder of the decade. Driven by AI adoption, capacity is expected to follow an 18.3% compound annual growth rate, scaling up to 4.5 gigawatts by 2030. To build this out, domestic and global capital is flooding the zone. In just a few years, the number of active hyperscale data center developers operating in India has jumped from 5 to 15. To sustain this sector's expansion, data centers are projected to consume roughly 4% of India's total incremental electricity demand over the next 5 years. But this gigawatt scale infrastructure cannot be built just anywhere. It is strictly tethered to the coastline. Data centers require immediate access to cable landing stations, the high-capacity fiber optic backbones emerging from the ocean that connect India's local cloud to the global internet backbone. This map illustrates how that single requirement forces severe geographic concentration. The vast majority of the nation's capacity is locked into just two cities, Mumbai holding 44% and Chennai holding 18%. Chennai has rapidly secured its position as the critical secondary hub, managing the data arriving along the eastern seaboard. It creates a deep irony. A technology designed to be invisible and borderless has resulted in one of the most concentrated, localized physical real estate and power bottlenecks in the country. That brings us back to Mumbai, the single largest power load hub for this new infrastructure. Even at today's baseline, data centers already consume a highly significant 13% of the city's total peak power demand. As new AI facilities come online, that number is set to surge. By 2030, data centers are projected to devour 28% of Mumbai's peak power capacity, over a quarter of the grid, swallowed by one industry. This localized drain creates an immediate secondary crisis. To keep the city's grid stable, Mumbai will require sustained infrastructure spending on battery energy storage systems and transmission corridors just to route electricity into the urban center. Right now, capacity sits at 1.3 gigawatts, using roughly 11 billion units of electricity. By 2030, capacity is projected to hit 4.5 gigawatts, tripling the required power drain to 39 billion units. India's current electrical grid is entirely unprepared to handle a localized bottleneck of this size. Rebuilding that infrastructure is going to trigger a massive investment cycle, creating a distinct wealth building opportunity that breaks down into three specific investment paths. Play number 1 focuses on the hardware integrators. These are the companies operating at the very tip of the spear, building and supplying physical servers and high-density computing racks directly to tech giants, expanding their footprint. These suppliers offer high reward potential, but they carry significant risk. Their stocks command steep valuation premiums, and their entire business model relies absolutely on complex global supply chains for advanced components like GPUs. This map shows the second play, the coastal utility monopolies. Unlike standard industrial demand, data centers require 24/7 power, and they aren't spread evenly across the country. 60% of India's installed capacity is clustered in just two specific cities, Mumbai and Chennai. Because they are confined to these coastal hubs, data centers act as permanent, premium-paying power consumers locked into specific local grids. Look at Mumbai, for example. Today, over 40% of India's entire data center capacity sits within this single city. By 2030, these server farms will consume nearly 28% of Mumbai's peak electrical demand. Upgrading the local grid to handle that much localized load requires massive capital expenditure. However, owning the infrastructure at this extreme geographic choke point grants the regional power distribution companies a highly lucrative, deeply entrenched financial moat. To understand how this plays out, we look at the United States as a historical blueprint. For over a decade, the US Utilities Index was effectively dead money, languishing under flat electricity demand and strict regulation. This tracks the US index. Notice the 2024 spike as investors realized AI data centers turned defensive utilities into high-growth assets. Layering Indian projections underneath, data center power demand grows from 0.7% today to 1.6% by 2030. India mirrors this US trajectory. There is a massive anomaly accelerating this timeline, however. Google is currently building a sprawling 1 gigawatt data center campus in the state of Andhra Pradesh. Because the facility requires such an immense constant draw of electricity, the state government granted Google a deemed DISCOM license. This status essentially allows Google to act as its own private power utility within its campus. This loophole means hyperscalers can procure their own renewable energy and bypass traditional local grids entirely. It proves that the massive wave of capital expenditure for next-generation power delivery has already arrived. That brings us to play number 3, battery energy storage systems, or BESS, and independent power transmission networks. These are the exact tools hyperscalers need to build their own independent grids. Since data centers require absolute round-the-clock uptime, BESS has become a mission-critical component of the power strategy. These systems actively shave down expensive peak demand costs and stabilize the fluctuating output of renewable energy into a consistent industrial-grade feed. Looking at this capacity forecast, you can see the scale of the physical build-out required. The Indian government projects battery energy storage demand will rocket to 236 gigawatt-hours by 2032. Investors now have to choose where they sit on the risk spectrum. You can bet on the volatile hardware suppliers, take shelter in the predictable cash flows of the monopolistic coastal utilities, or position yourself with the emerging battery storage providers. While software algorithms and AI chatbots capture the daily headlines, the true structural wealth in this transition lies in owning the physical copper and electrons that make those algorithms function. India's electrical grid is undergoing a complete rewrite to accommodate a massive new industrial consumer. The most profitable strategy is securing a position in that physical supply chain before the wider market fully prices in the battery. Energy storage systems represent the physical floor for India's digital ambitions. They provide the stabilization required to connect a renewable power grid to the specific high-intensity hardware that runs artificial intelligence. This diagram shows where electricity is actually used inside a data center. The IT equipment and cooling systems create a constant heavy load. Unlike traditional commercial buildings, hyperscale AI facilities contractually require 99.999% uptime, meaning they cannot tolerate a few seconds of power fluctuation. Meeting that demand with green energy creates a significant engineering challenge, as solar power generation drops to zero every evening, while the data center's power appetite remains constant. This makes battery storage a technical requirement for the grid. It acts as a physical bridge between intermittent daylight generation and the continuous power cycle demanded by AI server racks. At this scale, energy storage consists of massive industrial units. As the schematic shows, individual lithium ion cells are bundled into modules, organized into racks, and then housed within climate controlled shipping containers. These containers are sophisticated power management units. They use external cooling systems and safety controllers to perform three tasks at once: storing excess solar power during the day, integrating it into the grid at night, and managing peak demand spikes. To move this electricity into the wider network, these islands connect through low voltage transformers to dedicated grid substations. Without these physical buffers to stabilize the load, India's existing transmission lines cannot handle the concentrated power requirements of new hyperscale data center clusters. The necessity of this hardware is reflected in the sheer volume of storage capacity India must build over the next decade. This chart tracks India's battery storage capacity. We scale from just 0.5 gigawatt hours today to 174 gigawatt hours by 2030. By 2033, that requirement reaches 346 gigawatt hours, a compounded annual growth rate of 117%. Projections from the Central Electricity Authority suggest 236 gigawatt hours are needed by 2032 simply to maintain basic grid stability. This growth trajectory is significantly faster than traditional infrastructure development, creating a period of rapid capitalization for companies capable of manufacturing and installing this hardware. This demand is not based on market speculation. It is engineered by the state to ensure the digital economy has the power it needs. To build domestic manufacturing, the government provides an 18.1 billion rupee production-linked incentive. On the demand side, policy forces distributors to quadruple their storage obligations by 2030. To de-risk projects, the state offers viability gap funding and waives transmission charges through 2028. These combined measures remove the primary uncertainty for private capital. The policy framework treats energy storage as a regulated utility asset, providing the same demand visibility as traditional power infrastructure. While the policy provides the framework, a specific group of Indian corporations is now building the physical hardware for this ecosystem. Companies like Wari Energies and Exide Energy are establishing the core cell manufacturing and system integration capacity needed to meet these mandates. Large conglomerates are also making major investments, including Reliance Industries' Gigafactory in Delera and Adani New Industries' 300 billion rupee commitment in Mundra. The ecosystem also includes hybrid integrators like Premier Energies and Vikram Solar, alongside grid infrastructure companies like Polycab and KEI Industries, who provide the specialized cabling for these high voltage connections. The value in this shift is concentrated in the physical supply chain that makes these grid upgrades possible. For investors, the AI power demand creates three distinct paths based on risk tolerance and time horizons. The first path involves hardware integrators. These companies supply the direct components for AI facilities, carrying the potential for high growth alongside the risks associated with global supply chains. The second path focuses on cash flow stability. This involves the utility companies that hold monopolies in major data center hubs like Mumbai and Chennai. The third path is long-term capital. Battery storage and renewables currently offer the most transparent demand visibility of any infrastructure sector due to direct government mandates. While software receives the most attention, long-term AI profits are increasingly tied to companies building the physical infrastructure.